Welcome, fellow travelers of the cosmos. We begin an extraordinary journey, a voyage across time and space that starts with the very birth of the universe. From the first brilliant flash of the Big Bang to the formation of galaxies, stars, and worlds, we will trace the grand story of everything we know. Take a moment to look up at the night sky. Every star you see is a chapter in that story. And now, together, we turn the first page of this cosmic epic. In the beginning, there was nothing. No stars, no planets, not even time itself. Only silence and emptiness. But 13.8 billion years ago, an event occurred that gave birth to everything. From the smallest grain of sand beneath your feet to the countless galaxies shining in the night sky. We call this moment the Big Bang. From a single point, the universe was born, and ever since, it has been expanding. Imagine compressing the entire history of the universe into a single year. In this cosmic calendar, the Big Bang happens at midnight on January 1st. The first atoms form in January. The first stars ignite in March. Our solar system appears only in August. And humankind. We arrive in the final seconds of December 31st, just before the clock strikes midnight. In this journey, we will travel from that first spark of creation to the present day. We will witness how order emerged from chaos, how stars became the cradles of planets, and how the explosions of dying stars forged the elements that make up our very bodies. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were born in the fiery hearts of long-dead stars. This will be a long journey. We will cross epochs, from the first second after the Big Bang, through the Dark Ages, the birth of galaxies, the rise of the Milky Way, the formation of the Sun and Earth, all the way to the distant future, the possible fates of the cosmos, whether eternal expansion, collapse, or heat death. Prepare to feel the scale. What we call home is nothing more than a single grain of sand on the shore of an endless ocean. And tonight, we will plunge into that ocean to explore the history of the universe through the eyes of a cosmic traveler. This is a journey that begins in darkness, but leads us into the light. A journey through space and time, a journey through the history of the universe. In the darkness, there was no space, no time. There was no stage on which any story could unfold. The word before had no meaning, because time itself did not exist. Everything began with the moment we call the Big Bang. The Big Bang was not an explosion into empty space. It was the birth of space itself. Space stretched open, time began to flow, and energy poured outward. Imagine a spark that blossoms into light, but not inside an already existing hall of darkness, rather creating that hall in the very act of expansion. The very first instant is known as the Planck epoch, lasting less than 10 to the power of minus 43 seconds. At this scale, our laws of physics collapse. We know only one thing. All fundamental forces of nature were united into one. To imagine this, think of an orchestra. Picture a concert where instead of a melody, you hear only one overwhelming chord. You cannot distinguish the violins from the trumpets because all instruments are fused into a single sound. This is how the newborn universe behaved. Gravity, electromagnetism, and the strong and weak nuclear forces all played as one. Only later did they separate, like instruments taking on their own parts, bringing structure to the cosmic music. Around 10 to the power of minus 36 seconds, the universe entered a phase called cosmic inflation. The cosmos expanded billions of times in less than a heartbeat. Not because matter rushed through space, but because space itself was stretching. Tiny quantum fluctuations, random wrinkles in the fabric of reality, were magnified to cosmic scales. These wrinkles would later shape where galaxies would form and where vast voids would remain. When inflation ended, energy transformed into particles. The universe became a seething ocean of quarks, gluons, leptons, and photons. Particles and antiparticles were born in pairs and immediately annihilated. But here, the universe made its most important choice. Matter ever so slightly outnumbered antimatter, by just one particle in a billion. That tiny excess became everything: the stars, the planets, and us. A few microseconds later, about 10 to the power of minus 6 seconds after the beginning, quarks bound together into protons and neutrons. These were the very first building blocks of matter. The universe was still unimaginably hot, billions of degrees, and dense. Light existed, but it could not travel freely. Photons collided constantly with charged particles, trapping the cosmos in a blazing fog. At about 1 second after the Big Bang, neutrinos slipped free from the plasma, beginning their eternal journey. Even now, billions of them pass through your body every second, a silent whisper from the newborn universe still echoing across time. At that same moment, the balance between protons and neutrons froze. This ratio would soon allow the first atomic nuclei to form: helium, deuterium, and a trace of lithium. It was the next act in the great symphony of creation. So, in less than a single second after its birth, the universe already had its stage. The forces of nature, protons and neutrons, oceans of photons, and the faint background of neutrinos. This was only the first breath of the cosmos, but it was enough to make everything else possible. 1 second has passed since the birth of the universe. In that blink of time, it has already expanded billions of times, cooling just enough for chaos to begin forming patterns. Protons and neutrons, which had emerged in the first microseconds, now dominate the seething plasma. They are the basic building blocks of matter, freely drifting in the fiery ocean, ready to combine into the first atomic nuclei. Photons, particles of light, fill the young universe, but they cannot travel freely. They scatter constantly, colliding with electrons and bouncing back, locked inside a dense, radiant fog. The cosmos glows, but it remains opaque, like a furnace shrouded in mist. Neutrinos, however, tell a different story. Unlike photons, they have already broken free. Ghost-like and elusive, they rarely interact with anything. Even now, billions of them pass through every square centimetre of space and through our bodies, every single second. They are the silent messengers of that first second, carrying with them the memory of the universe's birth. At this stage, the universe is like a vast workshop. The tools are ready: protons, neutrons, photons, and neutrinos, and the energy is in place. Creation has not yet built stars, planets, or even atoms, but the blueprint is here. In these first seconds, The foundation for everything to come has already been laid. Between 1 and 3 minutes after the Big Bang, the universe entered a new chapter, the age of primordial nucleosynthesis. The temperature had fallen from billions of degrees to the point where protons and neutrons, the basic building blocks of matter, could finally bind together. Until this moment, collisions were so violent that every attempt at joining was instantly destroyed. But now, for the first time, stability was possible. In this brief window of time, the first atomic nuclei were born. Protons and neutrons combined to form helium-4, the most stable of the light elements. Smaller amounts of deuterium, a hydrogen nucleus with 1 neutron, tritium hydrogen with 2 neutrons, and a trace of lithium also appeared. These were the very first elements in the universe, the original alphabet from which all later chemistry would be written. But the furnace of the early cosmos was still too hot and too dense for heavier elements to form. Every attempt to build anything beyond lithium was shattered by the extreme energy of the environment. For now, the universe's chemical recipe was simple. About 3/4 hydrogen and 1/4 helium, with only whispers of other light nuclei. This moment may seem modest, but it was decisive. In just a few minutes, the cosmic balance of matter was fixed. Billions of years later, stars would ignite and use this mixture as their fuel. From these humble beginnings, hydrogen, helium, and traces of lithium, the path toward galaxies, planets, and life itself was set. The balance between protons and neutrons in the early universe may sound like a small detail, but in reality, it was decisive. Had this ratio been even slightly different, the universe we know today would not exist in its current form. Because of the conditions set in the first second, roughly 3 out of every 4 particles of matter became hydrogen. The remaining 1/4 formed helium nuclei, with only trace amounts of deuterium, tritium, and lithium. This precise balance, about 75% hydrogen and 25% helium by mass, became the chemical foundation of the cosmos. If the ratio of protons to neutrons had been altered, the outcome would have been radically different. With more neutrons, the universe might have produced far more helium, leaving little hydrogen for stars to ignite. With fewer neutrons, almost no helium would exist, preventing stars from forming stable nuclear reactions. Either way, a cosmos with different proportions would have been hostile to the emergence of galaxies, planets, and life. But in our universe, the numbers aligned perfectly. This primordial mix was not random. It was the recipe that allowed stars to shine. For billions of years, those stars would fuse hydrogen into helium, releasing the light and heat that made planets and eventually life possible. In this sense, the humble proton-neutron ratio, written into the first seconds after the Big Bang, determined the grand architecture of everything that followed. From the very first minutes, the universe had fixed its proportions of hydrogen and helium, the recipe that would one day fuel the stars. But although the ingredients were ready, the cosmos was still far from transparent. The young universe looked nothing like the clear night skies we know today. Instead, it was filled with a blinding, radiant fog, often called a cosmic milk. Photons, the particles of light, were everywhere, but they could not travel freely. Each time a photon tried to move, it was instantly scattered by an electron, absorbed or redirected. The result was an endless, shimmering mist, where light was trapped, unable to escape. This opaque state lasted not for seconds or minutes, but for hundreds of thousands of years. During this time, matter and radiation were locked together, inseparable. The universe expanded and cooled slowly, while photons remained prisoners in the cosmic fog. Only much later, when the temperature dropped enough for electrons to combine with nuclei and form neutral atoms, would the fog finally clear. At that moment, photons were released to travel freely through space. These ancient photons are still with us today, stretched into microwaves by cosmic expansion. We call them the cosmic microwave background, the afterglow of creation. So while the first seconds and minutes set the chemical foundation, the first hundreds of thousands of years kept the universe hidden behind a glowing curtain. The light of creation itself had to wait before it could finally break free and reveal the cosmos we can still observe today. Only a few minutes after the Big Bang, the particle era came to a close. By this time, the seething plasma of the early cosmos had cooled just enough for nuclear reactions to settle. The furious collisions of protons and neutrons had ended, leaving behind a stable mix of light nuclei. The chemical composition of the universe was now set. About 3/4 of its mass was hydrogen, 1/4 was helium, with only traces of deuterium, tritium, and lithium. This ratio would remain unchanged for billions of years. The primordial recipe written in the first pages of cosmic history. It may seem simple, a handful of light elements drifting through a dark, expanding fog. Yet from this simplicity would arise extraordinary complexity. Hydrogen and helium would one day collapse under gravity to ignite the first stars. Those stars, in turn, would forge the heavier elements: carbon, oxygen, iron, the ingredients of planets, oceans, and living beings. This moment was the first step in the grand alchemy of the cosmos. With the particle era finished, the stage was set. The universe had its raw materials. Now it only needed time and gravity to sculpt them into galaxies, worlds, and eventually, us. The particle era has ended. The primordial recipe of the universe has been written: hydrogen, helium, and traces of other light elements. The raw material for stars, planets, and eventually life itself is already in place. Yet, the cosmos remains dark and opaque. Photons are still trapped, unable to escape the fog of electrons. The first light of the universe has not yet broken free, and the skies remain without stars. This moment is both an ending and a beginning. The violent birth of particles has passed, but the stage is set for everything that follows. Gravity will soon gather these elements together, and in time, the first stars will ignite. A few minutes have passed since the dawn of time, and already the universe has determined the ingredients of all future creation. The blueprint for galaxies, worlds, and life is written in the language of hydrogen and helium. Now begins the long wait, the silent centuries of darkness, before the cosmos takes its next great step. Nearly 380,000 years after the Big Bang, the universe had expanded and cooled to about 3,000 Kelvin, roughly the heat of molten metal. For the first time, conditions allowed something remarkable to happen. Until this point, the cosmos had been a seething plasma, where free electrons roamed chaotically and photons were trapped in constant collisions. But now, as temperatures fell, electrons lost enough energy to settle into stable orbits around nuclei. This was the moment of recombination, when the first neutral atoms were born. Protons captured electrons to form hydrogen, the simplest and most abundant element in the universe. Helium, already forged during nucleosynthesis, also gathered electrons to become stable, neutral atoms. In this transformation, the universe changed from a brilliant but blinding fog into a calmer, more transparent place. With neutral atoms forming, the stage was set for the release of light, and the cosmos took one step closer to the clarity we know today. The formation of the first neutral atoms was far more than a chemical milestone. It was a cosmic revolution. For the first time, the universe became electrically neutral. Free electrons, which had once filled the plasma and trapped photons in endless collisions, were now bound into atoms. This simple change transformed the cosmos forever. With the electrons captured, photons, the particles of light, were suddenly free. No longer scattered at every step, they began to travel across space, uninterrupted. The dense fog that had shrouded the universe for hundreds of thousands of years dissolved, revealing a cosmos finally transparent. The disappearance of this cosmic milk marked a turning point. From this moment onward, light could move freely, carrying with it a record of the universe's earliest days. That faint glow has been stretched into microwaves by billions of years of expansion. Today, we still see it as the cosmic microwave background, the oldest light in the universe, a silent witness to creation itself. This was the moment when the universe ceased to be a blinding fog and became a window to its own history. What began as chaos and opacity was now transformed into clarity, setting the stage for the birth of stars and galaxies. When the first neutral atoms formed, something extraordinary happened. For the first time in cosmic history, photons broke free from matter. No longer trapped by constant collisions with electrons, they began an uninterrupted journey across the universe. This light, released nearly 380,000 years after the Big Bang, is still with us today. Over billions of years of cosmic expansion, its brilliant glow has been stretched into faint microwaves. We now observe it as the cosmic microwave background, or CMB, the oldest light in the universe. The discovery of the CMB in the 20th century was one of the greatest scientific milestones of modern astronomy. Detected first by accident in 1965, it provided direct and undeniable evidence that the universe began in a hot, dense state, just as predicted by the Big Bang theory. More than just ancient light, the CMB is a cosmic time capsule. Its faint ripples reveal tiny fluctuations in density, the seeds of galaxies, stars, and planets. Every photograph of the CMB sky is a map of the universe as it looked when it was only a few 100,000 years old. Thus, with the birth of the cosmic microwave background, the universe finally opened a window to its past. Light could at last tell the story of creation, and that story still shines upon us from every direction in the sky. Once the cosmic microwave background was released, the universe had finally become transparent. For the first time, light could travel freely, yet there was nothing new to shine. This was a paradoxical time. Space was no longer filled with blinding plasma, but instead with something far quieter: neutral atoms of hydrogen and helium. They drifted endlessly in the expanding void, invisible to the eye, offering no glow of their own. The fog had lifted, yet the skies were utterly dark. This era is called the Cosmic Dark Ages, and it lasted not for seconds, not for centuries, but for millions of years. Imagine looking at the universe then. There would be no stars, no galaxies, no planets, not even the faint glimmer of starlight on the horizon. Only the afterglow of the Big Bang, stretched and fading into the microwave spectrum, whispered across the void. Why was it dark? because the elements that existed, hydrogen and helium, were too simple to radiate visible light on their own. There were no processes yet to spark fusion, no gravitational giants to collapse into stars. The universe was like a theatre prepared for a performance, the stage set, the props in place. But the light still dimmed, the play not yet begun. And yet, in this seeming emptiness, something important was happening. Tiny variations in density, minute ripples imprinted in the cosmic microwave background, were now guiding matter under the pull of gravity. Slowly, atom by atom, cloud by cloud, these invisible seeds gathered mass. Dark matter, the hidden scaffolding of the cosmos, played its silent role, pulling hydrogen and helium into larger and larger clumps. It was a long gestation period, a cosmic pregnancy that would last hundreds of millions of years. The Dark Ages were the silence before the symphony, the pause before the first note. When the silence finally ended, it ended spectacularly. In the densest regions, gravity crushed hydrogen into the first stars, enormous, short-lived giants that burned with unimaginable brightness. Their light pierced the cosmic darkness, ending the Dark Ages and beginning the epoch of cosmic dawn. So, while the Dark Ages may sound like a void, they were in truth the foundation of everything to come. Without this long, quiet night, there would have been no morning, no stars, no galaxies, no us. The Dark Ages were not an ending, but a preparation. Out of the silent oceans of hydrogen and helium, the next chapter of the cosmos would be written. These simple elements, forged in the first minutes after the Big Bang, were destined for greatness. Over millions of years, gravity began to gather them into immense clouds. Invisible scaffolding of dark matter pulled the gas together, shaping knots and filaments across the expanding universe. Slowly, patiently, these clumps grew denser until deep inside their hearts, the first sparks of fusion ignited. Thus, the first stars were born. They were not small, gentle suns like ours, but colossal giants, hundreds of times larger, burning hotter and brighter than anything the universe had ever known. Their light pierced the cosmic night, ending the long silence of the Dark Ages and beginning the cosmic dawn. But their brilliance was more than illumination. Within their blazing cores, hydrogen and helium fused into heavier elements, carbon, oxygen, iron, the building blocks of planets, oceans, and life itself. When these titans died in violent explosions, they scattered their treasures into space, enriching the cosmos with the seeds of future worlds. In this way, the atoms created in the first minutes of existence became the foundation for galaxies, stars, and living beings. The universe had taken its next great step, from darkness into light, from silence into creation. And in the glow of the first stars, the path to everything we know today was set. After recombination, the universe had finally become transparent. The blinding fog of plasma had cleared, and for the first time, light could move freely across the vastness of space. Yet despite this new clarity, the skies remained utterly dark. There were no stars, no galaxies, no glowing clusters to shine in the night. The photons released during recombination, the cosmic microwave background, continued their journey, but no new sources of light existed to replace them. Instead, the universe was filled only with simple, neutral atoms of hydrogen and helium. These elements drifted silently through expanding space, invisible to the human eye. The cosmos was now clear, but empty of light, like a vast, transparent ocean in which nothing glimmered. This was the beginning of the cosmic Dark Ages, a long silent night that stretched for millions of years. It was not the end of the story, but the quiet prelude to the birth of the first stars. After recombination, the universe was transparent yet dark. Transparent because light was finally free to travel without being constantly scattered. Dark because there were no sources of new light, no stars, no galaxies, only a clear, silent cosmos in which nothing yet burned. It was like standing in a perfectly clean theatre, after the curtains have lifted, but before the first spotlight turns on. Every path for light is open, yet no lamp shines. The only glow was the ancient afterlight of the Big Bang itself. Those photons, released when the first neutral atoms formed, now free-streamed across space. With every moment of cosmic expansion, they were stretched to longer wavelengths and lower energies, shifting steadily out of the visible band into the microwave. If your eyes were tuned to microwaves, the whole sky would have seemed to glimmer evenly from every direction. To human eyes, it remained black. Meanwhile, no new photons were being made in visible light. The cosmos was filled almost entirely with neutral hydrogen and helium, simple atoms that, in this calm and diffuse state, did not glow. There were no hot stellar cores to fuse elements, no accreting black holes to blaze, no dense shocks to spark emission. The ingredients of light were present, but the furnace had not yet been lit. As the universe expanded, temperatures fell. The background radiation cooled from about 3000 Kelvin at recombination to a few tens of Kelvin over tens of millions of years, while the gas itself, no longer tightly coupled to the radiation, cooled even faster. With each drop in temperature, the darkness deepened. Matter became colder, the background light softer and redder, and the cosmic stage more hushed. And yet, this quiet was not empty of purpose. Tiny ripples in density, imprinted earlier in the fabric of space, began to guide matter under gravity's pull. Neutral hydrogen drifted towards slightly denser regions. Filaments and knots slowly took shape in the invisible scaffold of dark matter. The universe was transparent and dark, but it was not idle. It was preparing. This is the portrait of the Dark Ages. Clear paths for light, no lights yet lit. Photons on an endless journey, but no new beacons to join them. A steadily cooling cosmos gathering itself for the next act. Soon gravity would make the first fires, and the long night would give way to the cosmic dawn. During this era, the universe was transparent, but it was also blacker than any night we know. Imagine standing in a crystal clear room where every wall has been removed so that nothing blocks your view. And yet, there is no lamp, no candle, nothing to shine. That was the paradox of space in this age. Photons from the Big Bang still streamed across the cosmos, but they were no longer what they once were. With every moment of expansion, their wavelength stretched, like a note played lower and lower until it slips out of hearing. What had once been brilliant light became invisible microwaves, a silent hum in the background. Meanwhile, matter itself settled into neutrality. Hydrogen and helium atoms drifted through the void, simple and quiet. Unlike stars, these gases did not glow. They were cold, diffuse, invisible to human eyes. The cosmos was an ocean with no waves, a sea without reflections. As time passed, the temperature fell. What began as a searing 3000 kelvins soon dropped to hundreds, then tens. The cosmic radiation softened, the gases cooled, and the universe became like a vast freezer, its warmth drained into silence. This state endured for millions upon millions of years. It was a long waiting game, a transparent universe with no colors, no starlight, and no warmth. Yet this silence was only temporary. Beneath it, gravity was already working, preparing to light the first fires of the cosmos. Even in the apparent silence of the Dark Ages, the universe was not uniform. Within the cosmic microwave background, tiny fluctuations, variations in density no greater than 1 part in 100,000, were already imprinted on the fabric of space. These small differences, barely noticeable, carried the blueprint of everything that would one day exist. Gravity took hold of these ripples. In regions where matter was ever so slightly denser, atoms of hydrogen and helium felt the pull, drifting inward. Over millions of years, these gentle seeds became the birthplaces of stars, galaxies, and clusters. From faint whispers in the early cosmos, gravity sculpted the grand architecture of the universe. But ordinary matter was not alone in this process. Most of the weight of the cosmos belonged to something unseen: dark matter. It did not shine, it did not block light, but it shaped the universe all the same. Wherever dark matter was more concentrated, it created invisible wells of gravity into which hydrogen and helium could fall. Imagine the hidden beams of a building's skeleton. You cannot see them from outside, yet they hold the entire structure together. In this same way, dark matter created the hidden framework of the cosmos. Over time, this union of gravity and dark matter spun the first threads of the cosmic web. Vast filaments stretched across hundreds of millions of light years, separating immense empty voids. Along these filaments, matter gathered and would eventually ignite into stars and galaxies, tracing the grand design we can still observe today. Without these tiny fluctuations, amplified by the steady hand of gravity and the invisible mass of dark matter, the universe would have remained a featureless ocean of hydrogen and helium. No stars, no galaxies, no planets, no us. What began as faint ripples in the earliest light became the architecture of the living cosmos. Gravity transformed silence into structure, and randomness into the beginnings of order. After the first atoms formed and gravity began its patient work, the cosmos entered an era of profound stillness. No stars yet burned, no galaxies traced their luminous spirals, no black holes lurked in the depths. The universe was vast, transparent, and expanding, but it was a stage without actors. What filled this silent expanse was nothing more than hydrogen and helium, drifting in enormous clouds across billions of light years. To human eyes, it would have looked like a perfect emptiness. But this emptiness was not sterile. It was charged with potential. The raw ingredients for creation were there, scattered like invisible dust across an endless ocean. And yet, silence reigned. There was no starlight, no heat from blazing furnaces, no brilliant explosions to break the monotony. The universe resembled a great dark sea. Its only sound was the faint background whisper of ancient photons, radiation left over from the Big Bang, stretched by expansion into a quiet microwave hum. This was the cosmic silence, a night so deep it lasted for hundreds of millions of years. But beneath this quiet, forces were at work. Gravity was slowly gathering the gas into denser knots, and in time, the hush would be broken. The silence would not last forever. Out of this vast darkness, the first stars would soon ignite, and the universe would awaken. The cosmic dark ages began about 380,000 years after the Big Bang, when the universe had cooled enough for the first atoms to form. From this moment, the fog of plasma had cleared, leaving a transparent but starless sky. Light could travel freely, but there were no new sources of light to brighten the heavens. This silent era stretched on for an unimaginably long time. For 100 to 200 million years, the universe remained without stars, without galaxies, and without the brilliant beacons we associate with the cosmos today. In human terms, this period lasted hundreds of times longer than the entire recorded history of our civilization. During this vast span, the universe was expanding, cooling, and waiting. Matter drifted slowly under the guidance of gravity, gathering into denser regions, but the process was agonizingly slow. To an observer, it would have felt like an endless night that refused to break, a cosmic slumber stretching across aeons. The duration of the Dark Ages was crucial. It gave the universe time to calm, to allow matter to settle into structures that could one day ignite. The long night was not wasted time, it was a preparation. When it finally ended, the silence would give way to the light of the first stars, and the cosmos would awaken into its next great chapter, the cosmic dawn. For hundreds of millions of years, the universe had remained silent and dark. But eventually, gravity's patient work reached a tipping point. Clouds of hydrogen and helium, gathered by invisible threads of dark matter, grew denser and hotter until something extraordinary happened: the birth of the very first stars. These primordial stars, far larger and more powerful than most stars today, were blazing furnaces that ignited against the blackness. For the first time since the Big Bang, the cosmos had new sources of light. Their radiation pierced the darkness, transforming the universe from an ocean of shadows into a landscape dotted with brilliant beacons. This period is known as the cosmic dawn, the moment when the long night ended. The light of the first stars did more than shine. It changed the fabric of the universe itself. Ultraviolet radiation from these giants began to reionize the neutral hydrogen around them, making space once again an active and glowing environment. From that moment onward, the Dark Ages were over. The silence was broken, and the appearance of starlight reshaped the cosmos forever. The universe had awakened, no longer an empty stage, but a living, radiant theater filled with the first sparks of creation. Out of a silent ocean of hydrogen and helium, gravity began to find its footing. The early cosmos was not perfectly even. Tiny overdensities, ripples written into space itself, acted like shallow basins. Atom by atom, gas drifted toward these basins, and the emptiness started to gather shape. Invisible mass did the heavy lifting. Dark matter concentrated first, forming broad, soft wells of gravity, small halos that weighed hundreds of thousands to 1 million solar masses. Around these unseen anchors, ordinary gas collected. The camera would see nothing glowing, yet feel the pull everywhere. An architecture you cannot look at, only enter. As hydrogen and helium fell into a halo, they were squeezed and heated by shocks until the gas reached its settled state. Astronomers call it virialization, at temperatures of a few thousand Kelvin. But heat creates pressure, and pressure resists collapse. For the gathering to continue, the gas needed a way to cool. In the dark, chemistry quietly switched on. A handful of leftover electrons helped hydrogen build molecular hydrogen, H2, rare, fragile, but precious. H2 can radiate away energy even in this metal-free universe. With that coolant, the gas bled heat, slipping from thousands of Kelvin down to a few hundred Kelvin. Cooling lowered the pressure, letting gravity tighten its grip. Now the balance tipped. As temperature fell and density rose, the gene's mass, the minimum lump that can collapse under its own gravity, shrank. The once gentle cloud fragmented. Filaments fed dense knots, and the densest knot became a protostellar core. Angular momentum spun up a disk around it, Streams of gas spiraled inward like rivers into a whirlpool, feeding the growing seed. Deep inside that core, numbers climbed, densities soared, the pressure mounted, and the temperature raced upward again. Not from shocks this time, but from inexorable compression. The collapse slowed only where radiation could no longer carry heat away fast enough. There, the core turned opaque, trapping energy, tightening further. Everything to this point was preparation, the quiet engineering of a furnace. When the central temperature climbed into the millions of Kelvin, the conditions for a new kind of fire were in place. The simplest element, hydrogen, was about to light the first stars. At last, the collapse reached its climax. Deep within the densest knots of gas, the temperature soared into the millions of Kelvin. Pressure squeezed every atom tighter and tighter, until hydrogen nuclei, protons, could no longer resist. They smashed together, overcoming their mutual repulsion. This was the beginning of nuclear fusion. For the very first time since the Big Bang, new energy was being created inside stars. Hydrogen fused into helium, and with each reaction, a small fraction of mass was transformed into pure energy, exactly as Einstein had predicted with E equals mc squared. The result was staggering. Within moments, the core that had been cold and invisible blazed into a radiant furnace. Rivers of photons burst outward, trying to escape, while streams of neutrinos slipped silently through space. The star's light broke free, flooding into the dark void around it. These first stars were titans. Their energy output dwarfed anything the cosmos had yet seen. In their blazing hearts, light and heat poured forth in unimaginable quantities, turning patches of the universe into islands of brilliance. With fusion, the silence was shattered. The universe now had its first true beacons, stars that lit the cosmic dawn, and began the long chain of creation that would one day lead to galaxies, planets, and life itself. The very first stars, known as population 3 stars, were unlike almost anything we see today. Forged entirely from hydrogen and helium, the only elements born in the Big Bang, they carried none of the heavier elements that enrich modern stars. This made them fundamentally different, primitive giants standing at the dawn of cosmic history. They were immense in size, far more massive than most stars we know. Many were dozens, and some possibly hundreds of times the mass of our Sun. Their great size meant that gravity crushed their cores to extreme conditions, producing staggering amounts of energy. These titans of fire shone with a brilliance unmatched by ordinary stars. But their greatness came at a cost. The more massive a star, the faster it burns its fuel. And so these giants lived not for billions or even hundreds of millions of years, but for only a few million years at most. A fleeting instant on cosmic timescales. They blazed fiercely, lived briefly, and then collapsed or exploded, leaving behind black holes or dispersing their material into space. Their light was predominantly ultraviolet, far more energetic than the light from our Sun. This radiation poured into the surrounding hydrogen, ionizing and heating it. Entire regions of the universe were reshaped by their glow. The ultraviolet output of these stars marked the beginning of the epoch of reionization, a transformative period when the cosmos shifted from darkness to a universe filled with light and structure. Though none of these population 3 stars are alive today, their legacy endures. Every heavy element in our bodies, the carbon in our cells, the oxygen we breathe, the iron in our blood, exists because those first stars lived fast, died violently, and seeded the cosmos with the ingredients of life. In their short and brilliant existence, they lit the path forward for everything that would follow. The arrival of the first stars transformed the universe forever. For hundreds of millions of years, space had been silent, dark, and cold. But when these giant pioneers ignited, they brought an end to the cosmic night. Their brilliance marked the cosmic dawn, a turning point when the universe was no longer a sea of shadows, but a living stage illuminated by countless suns. Their light carried immense power. The ultraviolet radiation streaming from these stars struck the neutral hydrogen around them, tearing electrons from their atoms. This process, known as cosmic reionization, changed the very state of the universe. Regions of space that had once been calm and opaque began to glow and open, clearing the way for future galaxies and structures to form. The first stars were not just sources of light. They were architects of transformation. And when their short lives ended, they exploded with ferocity as supernovae. In these cataclysms, the first heavy elements were forged: carbon, oxygen, iron, and more. These elements, scattered into the cosmos, became the raw material for everything to come. Planets, oceans, and eventually life itself traced their origins back to those first brilliant furnaces.
The importance of the first stars cannot be overstated. They were the ones who ended the silence, reshaped the chemistry of the universe, and gave it the tools to build complexity. Every atom of iron in your blood, every molecule of oxygen you breathe, every grain of dust that formed our planet, all were born from the death of these ancient giants. They lit the way forward, and in doing so, made our existence possible.
Without the first stars, there would have been no future generations of galaxies. They were the architects of complexity in a universe that had once been nothing but hydrogen and helium. By igniting and then dying, they seeded the cosmos with the building blocks of everything that came after. Every atom of oxygen you breathe, every carbon atom in your cells, every speck of iron flowing through your blood, all of them were born in the hearts of those first stars and scattered across space in their explosive deaths. Their short lives created the raw material for planets, oceans, atmospheres, and eventually life itself. These stars became the first cosmic lanterns, ending the primordial darkness and setting the stage for everything that followed. They forever changed the appearance of the universe, turning it from a silent sea of shadows into a vibrant expanse filled with light, chemistry, and possibility. Their legacy endures in every galaxy, every star, every planet, and within us. After the birth of the first stars, the universe was no longer uniform. Light and energy from those giants had begun to shape their surroundings, leaving pockets of heated gas and regions of cooling matter. What had once been a smooth sea of hydrogen and helium now showed texture, ripples, and imbalance. Gravity seized the opportunity. Wherever gas and stars gathered, its pull grew stronger, drawing in more material. Clouds of hydrogen thickened, streams of gas converged, and clusters of stars formed. Piece by piece, matter began to assemble into larger, more complex structures. But behind the scenes, the true scaffolding of this growth was invisible. Dark matter, the unseen majority of mass in the cosmos, had already collected into vast halos. These halos acted like cosmic skeletons, silent frameworks that ordinary matter clung to. Within these dark structures, gas and stars found shelter, gathering into the seeds of galaxies. The stage was set. Out of darkness and disorder, the universe was preparing to build its first great cities of light, the galaxies. The first true galaxies did not appear fully formed. Instead, The early universe gave rise to small, fragile structures, proto-galaxies. These were loose gatherings of stars and gas clouds, lacking clear shapes or defined structures. They were clumps of light within the darkness, cosmic experiments on the way to something greater. Proto-galaxies did not exist in isolation. Drawn by gravity, they slowly drifted toward one another. When they collided, their gas merged, their stars mixed, and the structures grew larger. Each merger was a step toward complexity, a rehearsal for the grand galaxies we know today. Yet, compared to modern galaxies, they were tiny. While today's Milky Way contains hundreds of billions of stars, a proto-galaxy might have held only a fraction of that number, perhaps a few million or tens of millions. Still, within these modest beginnings lay the seeds of everything to come. They were the building blocks of the cosmic architecture, destined to merge and evolve into the massive spiral and elliptical galaxies that now fill the night sky. In the young universe, collisions were not rare events. They were the rule. Proto-galaxies frequently crashed into one another, their stars and gas pulled together by gravity. Each encounter reshaped them, tearing apart their fragile structures and merging them into larger, more complex systems. Out of this chaos, new order began to emerge. As these mergers continued, the power of gravity sculpted structure. Some growing galaxies flattened into disks, their stars and gas spiraling around a common center. Others became more spherical, developing vast halos of stars bound by invisible dark matter. These interactions were the early architects of the familiar galaxy shapes we see in the cosmos today. But the story was not only about structure, it was also about chemistry. Inside these proto-galaxies, the most massive stars lived fast and died violently. Their deaths as supernovae blasted heavy elements, carbon, oxygen, iron, into the surrounding space. With every explosion, the environment became richer, seeding the raw material for planets, future generations of stars, and eventually life itself. Mergers and growth were the crucible in which the universe forged its first great cities of light. Galaxies. As the early universe matured, the chaotic proto-galaxies began to settle into recognizable forms. Some of them flattened into vast disk-like structures, where gas and stars spiraled gracefully around their centers. These glowing formations were the ancestors of today's majestic spiral galaxies, like the Milky Way. Their symmetry and order were born from billions of years of gravitational balance. Not all galaxies followed this path. Others grew through repeated collisions, swelling into enormous spherical or elliptical clusters. These systems lacked the elegant spiral arms, but their dense, rounded structures shone with the light of countless stars packed tightly together. Even in their simplicity, they embodied grandeur, becoming massive galactic giants that dominated their regions of space. At the heart of many of these young galaxies, something even more powerful was stirring. Black holes, likely formed from the collapse of the earliest massive stars, began to anchor galactic centers. Though invisible themselves, their influence was immense. They regulated the flow of gas, shaped star formation, and sometimes blazed as quasars. Beacons so bright they outshone entire galaxies. The emergence of these galactic forms marked a new stage in cosmic history. The universe was no longer a scattering of fragile clumps. It had organized itself into spirals, ellipses, and brilliant cores, structures that would endure for billions of years and define the cosmic landscape we see today. By the time the universe reached the age of 1 to 2 billion years, it was entering a remarkable phase of transformation. The quiet beginnings of proto-galaxies gave way to an era of furious construction. Everywhere across the cosmos, matter was assembling into larger and more organized systems. Galaxies became factories of stars, producing them at an astonishing rate. Clouds of hydrogen collapsed by the millions, igniting nuclear furnaces and filling galaxies with fresh light. Starburst regions, colossal clusters of young, hot blue stars, blazed across the heavens, their radiance spilling into intergalactic space. This was the peak of cosmic creativity, when the universe's energy was focused on building stars faster than at almost any other time in its history. Small clumps of gas and stars that had once drifted in fragile formations now merged and grew into vast, complex structures. Tiny proto-galaxies evolved into the grand galaxies we recognize today, spirals with graceful arms and ellipticals shining with dense cores. During this epoch, the first large-scale architecture of the universe came into focus. The foundations of clusters, superclusters, and eventually the great cosmic web that still defines the structure of the cosmos. It was a golden age of growth, when the universe was still young, but already full of vitality, laying the groundwork for billions of years of galactic evolution to come. Without the first galaxies, the universe would never have grown into the vast structures we see today. They were the foundations upon which everything larger was built, from star clusters and giant galactic groups to enormous superclusters stretching across hundreds of millions of light years. The very architecture of the cosmos began with them. Inside these early galaxies, the stage was set for the second generation of stars. Enriched by the heavy elements from the first supernovae, new stars were born with the ability to form planets around them. From these environments came the ingredients for oceans, atmospheres, and, eventually, life itself. In this way, galaxies became not just collections of stars, but cradles of possibility. The first galaxies were the cosmic building blocks, bricks in the grand design of the universe. Through their mergers, their star formation, and their chemistry, they created the conditions that shaped everything to come. From the majestic spirals and massive ellipticals to the planets under our feet, all trace their origins back to these ancient structures. The story of the first galaxies is, in a very real sense, the story of us.
We have traced the story of galaxies, their birth from fragile clouds, their collisions and their growth into the magnificent spirals and ellipticals that paint the night sky. But hidden beneath this grand architecture lies a deeper mystery, one that galaxies themselves cannot explain. For as vast as they appear, the stars and gas we see are only a fraction of reality. To truly understand the universe, we must step beyond the visible and confront the unseen forces that dominate the cosmos. This is the realm of dark matter and dark energy. Modern science has revealed a staggering truth. Over 95% of the universe is invisible to us. The stars, planets, and nebulae, everything that shines, make up less than 5% of all cosmic matter and energy. The rest belongs to two great mysteries, dark matter and dark energy. It is important to see them not as the same thing, but as two distinct phenomena. Dark matter acts like a hidden skeleton, its gravity binding galaxies and shaping the cosmic web. Dark energy, on the other hand, works in the opposite direction, driving the accelerated expansion of space itself. One pulls together, the other pushes apart. Understanding this balance between the unseen matter that builds and the unseen energy that expands is the key to unlocking the true nature of the cosmos. And so, our journey now shifts into the invisible universe, where most of reality hides. Dark matter is one of the greatest enigmas of modern science. Unlike the stars and nebulae that shine in the night sky, dark matter neither emits nor absorbs light. It is completely invisible to our telescopes. If you were to look directly at it, you would see nothing, a hidden fabric woven into the cosmos. And yet its presence is undeniable. We cannot see dark matter itself, but we can see its gravitational fingerprints everywhere. Stars at the edges of galaxies move far faster than they should, as if pulled by an unseen hand. Entire clusters of galaxies are held together by a mass far greater than the visible matter inside them. This invisible glue is dark matter. Astronomers have also witnessed dark matter's effects through a phenomenon called gravitational lensing. When light from distant galaxies passes through regions rich in dark matter, the unseen mass bends and distorts the light, much like a giant cosmic magnifying glass. We don't observe the dark matter directly, but we see how it warps space itself. In short, dark matter is invisible, but its influence is everywhere. Without it, galaxies would fly apart, the cosmic web would never have formed, and the universe would look nothing like it does today.
Dark matter is more than an invisible presence. It is the framework upon which the universe was built. Think of it as a hidden skeleton, stretching across cosmic scales, giving structure to everything we see. Galaxies, clusters, and even the great cosmic web itself are all anchored to this unseen foundation. Without dark matter, galaxies as we know them could not exist. The visible stars and gas within a galaxy simply don't have enough mass to hold themselves together. They would drift apart, dispersing into the void. It is only the additional gravitational pull of dark matter that keeps them bound, allowing spirals, ellipticals, and clusters to survive for billions of years. On the largest scales, dark matter has woven the cosmic web. Immense filaments and nodes where galaxies gather, separated by vast voids. These filaments are not just patterns of stars. They are the scaffolding of the universe, created by dark matter's silent influence. Every galaxy, including our own Milky Way, rests within these threads of an invisible design. Dark matter is, in a sense, the architect of the cosmos. It does not shine, yet it is the silent force that shaped the grand structures of space. Although dark matter itself is invisible, astronomers have developed ingenious ways to detect its presence through the effects it leaves behind. The first major clue came from the pioneering work of Vera Rubin in the 1970s. She studied the rotation curves of spiral galaxies and found something astonishing. Stars at the outer edges were orbiting just as fast as those near the center. According to the laws of physics, those outer stars should have been flung into space. The only explanation was an unseen mass surrounding the galaxy. A massive halo of dark matter. Another method is through gravitational lensing. According to Einstein's theory of relativity, mass bends light. When light from a distant galaxy travels past a large clump of dark matter, its path warps, stretching the galaxy's image into arcs or rings. We cannot see the dark matter itself, but the distorted light is clear evidence of its gravitational power. Finally, dark matter reveals its fingerprints in the cosmic microwave background, the faint afterglow of the Big Bang. By mapping tiny variations in this ancient light, astronomers can trace how dark matter was distributed in the early universe. These patterns helped shape the cosmic web, guiding the formation of galaxies and clusters. Through galaxy rotation, gravitational lensing, and the ancient cosmic light, we catch glimpses of the invisible and slowly piece together the story of dark matter. To explain the invisible mass of the universe, physicists have proposed several candidates for what dark matter might actually be made of. None have been confirmed, but each tells us something about the possibilities hidden within the quantum world. One leading idea involves WIMPs, weakly interacting massive particles. These hypothetical particles are thought to have mass, but interact so rarely with ordinary matter that they pass straight through stars, planets, and even our own bodies without leaving a trace. Experiments deep underground have searched for tiny collisions between WIMPs and atomic nuclei, but so far, no definitive signal has been found. Another intriguing possibility is the axion, an extremely light, ghost-like particle. Axions were originally proposed to solve a problem in particle physics, but they also turned out to be strong candidates for dark matter. If they exist, axions could subtly transform into photons in the presence of strong magnetic fields, a phenomenon scientists are trying to detect with ultra-sensitive laboratory experiments. A third contender is the sterile neutrino. Unlike the familiar neutrinos produced in the Sun or nuclear reactors, sterile neutrinos would not interact via the weak force at all, making them even harder to detect. They might leave faint signatures in the X-ray sky, but so far, the evidence remains inconclusive. The challenge is that despite decades of effort, from particle accelerators to satellite observatories, none of these candidates has been proven to exist. Each remains a compelling possibility, but the true identity of dark matter continues to elude us. Until we capture direct evidence, it remains one of the greatest unsolved mysteries in science. In 1998, astronomers made a discovery that changed our understanding of the universe forever. By observing distant supernovae, they expected to see the expansion of the cosmos slowing down under the pull of gravity. Instead, they found the opposite. The expansion was speeding up. Something unknown was pushing galaxies apart. This force became known as dark energy. Dark energy acts like a kind of anti-gravity. While dark matter pulls galaxies together, dark energy pushes the fabric of space itself outward. It is not a force we can see or touch, but its effect is written across the universe. Every distant galaxy is racing away from us faster and faster. Today, scientists estimate that dark energy makes up about 68% of the total energy and mass of the cosmos. That means nearly 7/10 of everything around us is this mysterious, invisible phenomenon. We don't know what it is, only that it dominates the destiny of the universe. Dark energy remains the greatest mystery in modern cosmology. It is the silent driver of cosmic expansion, shaping the future of everything that exists. Even though dark energy is invisible, astronomers have found ingenious ways to measure its effects on the universe. One of the most powerful tools is the use of Type 1a supernovae as standard candles. These stellar explosions shine with nearly identical brightness wherever they occur. By comparing their true brightness to how faint they appear from Earth, scientists can calculate their distance. In 1998, these supernovae revealed that galaxies were not slowing down in their expansion. They were accelerating, providing the first direct evidence of dark energy. Another method involves mapping the large-scale structure of the cosmos. Galaxies are not randomly scattered. Instead, they form vast clusters and filaments. By studying the distribution of these structures across billions of light-years, astronomers can see how dark energy influences the growth and arrangement of matter in the universe. Finally, the cosmic microwave background, CMB, the faint afterglow of the Big Bang, carries subtle imprints of dark energy. By measuring tiny fluctuations in this ancient light, satellites like WMAP and Planck have given scientists precise estimates of how much of the universe is dark energy. Through supernovae, galaxy surveys, and the CMB, we measure what cannot be seen directly. And each method points to the same profound conclusion. Dark energy dominates the fate of the cosmos. The greatest mystery of dark energy lies not only in what it is, but in what it means for the future of the cosmos. If dark energy continues to behave as it does today, the universe will undergo eternal accelerated expansion. Galaxies will drift farther and farther apart, until one day even the closest galaxies vanish beyond our horizon, leaving the night sky dark and empty. But this is not the only possibility. Some cosmologists have proposed the idea of a Big Rip. In this scenario, dark energy grows stronger with time, tearing apart galaxies, stars, planets, and eventually even atoms themselves, in a final catastrophic unraveling of reality. On the other hand, if dark energy behaves differently than we expect, there might be a big crunch. In this fate, expansion slows, halts, and then reverses, pulling the universe back in on itself until it collapses in a fiery end, possibly giving birth to another cycle of cosmic rebirth. The truth is, we do not yet know which path awaits us. Our knowledge of dark energy is still in its infancy. Whether the universe expands forever, rips apart, or collapses back into darkness remains one of the most profound questions in modern cosmology. And perhaps the ultimate key to our destiny among the stars. Dark matter and dark energy are two of the most mysterious components of the cosmos. They are not the same thing, yet together they form what scientists call the invisible universe. Dark matter acts as the cosmic framework. It provides the hidden gravitational scaffolding that allows galaxies and galaxy clusters to form and hold together. Dark energy, on the other hand, is the force that drives the accelerated expansion of space, pushing galaxies farther apart. It behaves like a vast pressure, counteracting gravity on the largest scales. When we look at the cosmic inventory, the numbers are astonishing. About 27% of the universe is dark matter, about 68% is dark energy, and only roughly 5% is ordinary matter. Everything we can see, from stars and planets to people. Together, dark matter and dark energy govern the shape, growth, and ultimate fate of the universe. They are distinct phenomena, but their combined influence defines nearly all of cosmic history, leaving the familiar world of atoms as only a tiny fraction of the whole. Solving the mysteries of dark matter and dark energy would do more than complete our map of the universe. It would transform our understanding of reality itself. If we can discover what these invisible components truly are, we will rewrite the very foundations of physics. The laws that describe space, time, and gravity might need to be expanded or completely reimagined. New forces or particles beyond today's standard model could emerge, offering a deeper picture of how nature works. The implications reach far beyond science. For philosophy, the revelation would reshape our concepts of existence and our place in the cosmos. Questions once confined to metaphysics. What is the universe made of? What is the fate of everything? Would be met with real, testable answers. Together, dark matter and dark energy form the hidden majority of the cosmos, about 95% of all mass and energy. To understand them is to approach the ultimate portrait of the universe, a vision that unites observation, theory, and human curiosity into a single, profound truth. On a clear night, far from city lights, a pale river of stars arcs across the darkness. This glowing band is our cosmic home, the Milky Way galaxy. Every point of light you see is a sun, and beyond them lie countless others hidden in the faint mist. The Milky Way is both familiar and profoundly mysterious. It is the galaxy that cradled our solar system and gave rise to life on Earth. Astronomers have mapped its spiral arms, measured its vast dimensions, and even glimpsed the supermassive black hole at its center. Yet enormous questions remain. How did it assemble from clouds of ancient gas? How much invisible dark matter holds it together? What future awaits this immense island of stars? To explore the Milky Way is to look both outward and inward. Outward to the grand structure of the cosmos, and inward to the story of our own origin. As we begin this journey, we stand beneath the same shimmering band that inspired poets, navigators, and dreamers for millennia. The Milky Way is a majestic barred spiral galaxy, a rotating island of stars, gas, and dark matter. From end to end, it stretches roughly 100,000 light-years across, its luminous disk appearing as a thin glowing band when viewed from inside. Astronomers estimate that the Milky Way contains between 200 and 400 billion stars, each with its own planets, moons, and possible worlds. Among these countless suns, our own solar system orbits within one of the galaxy's spiral arms, known as the Orion Arm. We reside about 27,000 light-years from the galactic center, roughly halfway between the core and the outer edge, completing one full orbit around the center every 225 to 250 million years. This immense structure is not static. Stars, gas clouds, and dark matter swirl together in a vast cosmic dance, shaping the Milky Way's graceful spiral pattern and sustaining the environments where new stars continue to be born. The Milky Way is not a single flat sheet of stars, but a complex layered system with three main components: the galactic disk, the central bulge, and the halo that surrounds them. The galactic disk is the most striking feature. Here, long spiral arms wind gracefully around the center, filled with young, hot stars, glowing nebulae of gas, and lanes of interstellar dust. This is the region where new stars continue to form, shaping the bright band we see across our night sky. At the heart of the galaxy lies the bulge, a dense, football-shaped hub of older stars and interstellar gas. It is home to the Milky Way's supermassive black hole, Sagittarius A star, whose gravity organizes the motion of the entire galaxy. The bulge is crowded and turbulent, a stark contrast to the quieter spiral arms. Surrounding both disk and bulge is the vast halo. This faint, nearly invisible sphere contains ancient, metal-poor stars and hundreds of globular clusters, compact swarms of stars that date back to the galaxy's earliest days. Even more mysterious, the halo is suffused with dark matter, an unseen substance whose gravity helps hold the Milky Way together. Together, these layers create the grand architecture of our home galaxy. A vibrant disk of ongoing starbirth, a central bulge anchored by a giant black hole, and a ghostly halo of old stars and hidden mass. At the very heart of the Milky Way lies a hidden giant, Sagittarius A, a supermassive black hole with a mass about 4 million times that of our Sun. Although completely invisible, its presence is undeniable. Astronomers confirmed this cosmic monster by watching the motions of stars that orbit an unseen point near the galaxy's core. Over years of patient observation, they tracked stars racing around an apparently empty region at astonishing speeds, some completing an orbit in just over a decade. Only an object with millions of solar masses packed into a space smaller than our solar system could create such gravitational power. The black hole itself emits no light, but surrounding gas and dust occasionally flare as they spiral inward, releasing bursts of X-rays and infrared radiation. These signals allow us to study the extreme physics of gravity at the very limits of known science. Sagittarius A anchors the Milky Way, shaping the orbits of stars and influencing the evolution of the entire galaxy, silently ruling from the darkness at its core. The Milky Way's luminous disk is threaded with majestic spiral arms, each one a river of stars and nebulae winding around the galactic center. Astronomers identify several main arms: the Perseus arm, the Sagittarius arm, the Cygnus arm, and others, all interconnected by smaller spurs and bridges of starlight. These sweeping structures are not rigid. They are patterns of density where stars and gas gather, creating the grand spiral we see from within. Within these arms lies a striking contrast of stellar populations. The bright blue glow of young, massive stars lights up giant clouds of hydrogen gas, signaling active star formation. These newborn suns burn hot and live fast, surviving only a few million years. Beyond the crowded arms, in the galaxy's halo, the stars tell a much older story. Here reside ancient, metal-poor stars and dense globular clusters, remnants from the Milky Way's earliest era. Cooler and dimmer, they have persisted for billions of years, serving as cosmic fossils that reveal the galaxy's long and complex history. Together, these vibrant spiral arms and the quiet halo weave a living tapestry, a galaxy where fiery youth and ancient age coexist, shaping the Milky Way's continuing evolution. The Milky Way is not a static collection of ancient stars. It is a galaxy that changes its chemistry over time. Every generation of stars acts like a cosmic forge, fusing light elements, mainly hydrogen and helium, into heavier ones deep in their cores. When the most massive stars reach the end of their brief lives, they die in spectacular supernova explosions. These titanic blasts scatter newly forged elements, carbon, oxygen, silicon, iron, into the surrounding interstellar gas. Over billions of years, countless supernovae have enriched the galaxy's clouds of gas and dust with these heavy elements, transforming the Milky Way into a more complex and life-friendly environment. From this enriched material, new generations of stars and planets are born. The Sun itself, along with Earth and everything on it, formed from gas already seeded by earlier supernovae. The calcium in our bones, the iron in our blood, and the oxygen we breathe all originated in the fiery deaths of long-vanished stars. Chemical evolution is therefore a continuing cycle. Stars create the elements, supernovae disperse them, and new stars and worlds emerge from the enriched debris. Through this process, the Milky Way has gradually transformed from a simple hydrogen-helium galaxy into the diverse chemical landscape we see today, a galaxy capable of hosting life. The Milky Way is not a static pinwheel of stars. It is a rotating, gravitationally bound system whose motion reveals some of the universe's deepest mysteries. The entire galaxy spins like a colossal cosmic wheel. Stars in the disk, including our Sun, orbit the galactic center once every 225 to 250 million years. Remarkably, stars far from the center move nearly as fast as those closer in, defying the expectations of visible gravity. This unexpected rotation pattern is one of the clearest signs that the Milky Way is threaded with dark matter, an invisible substance whose gravity provides the extra pull needed to keep the galaxy together. Our own solar system races around the galactic core at an average speed of about 828,000 kilometers per hour, roughly 514,000 miles per hour. At that pace, we travel nearly 230 million kilometers every single day. Yet we never feel this motion, because everything around us shares the same vast orbit. This grand rotation shapes the galaxy's spiral arms, stirs giant clouds of gas and dust, and drives the slow mixing of stars and elements over billions of years. The Milky Way is a living, moving structure, a silent dance of matter, both visible and unseen, across the dark expanse of space. The Milky Way is not an isolated island in space. It belongs to a small cosmic family known as the Local Group, a gravitationally bound cluster of more than 50 galaxies. This group includes our nearest large neighbors, the Andromeda Galaxy, M31, and the Triangulum Galaxy, M33, as well as dozens of dwarf galaxies that orbit the larger members like satellites. Over billions of years, these galaxies interact through gravity, pulling gently on each other across millions of light years. Streams of stars and gas connect them, a silent reminder that even galaxies are part of a wider web of relationships. The most dramatic chapter of this neighborhood story lies in the future. In roughly 4 billion years, the Milky Way and Andromeda are destined to collide and merge. This will not be a violent crash of solid objects. Stars are far too spread out for that. Instead, the two galaxies will pass through one another, their shapes warping into long tidal tails before settling into a single, giant elliptical galaxy, sometimes nicknamed Milkomeda. During this slow dance, our own solar system will likely drift to a new position within the merged galaxy, while new waves of star formation light up the night skies of that far-off era. The local group will gradually become one immense structure, reshaping the appearance of our cosmic home forever. To understand the Milky Way, astronomers use a full spectrum of observation techniques, each revealing a different layer of our galaxy's story. Optical telescopes capture the visible light of stars and nebulae. From historic observatories on mountaintops to giant modern instruments like the Very Large Telescope in Chile, they provide crisp images of star clusters, spiral arms, and distant nebulae. Radio astronomy peers into regions hidden by interstellar dust. Massive radio dishes such as the Green Bank Telescope and the Atacama Large Millimeter Array detect the faint emissions from cold gas clouds, pulsars, and the supermassive black hole at the galaxy's core. Above Earth's atmosphere, space observatories, including the Hubble Space Telescope, the James Webb Space Telescope, and X-ray missions like Chandra, observe wavelengths impossible to see from the ground. They reveal everything from newborn stars in dusty nurseries to high-energy phenomena near black holes. One of the most revolutionary projects is the Gaia mission, which has mapped the precise positions and motions of more than 1.8 billion stars. Gaia's vast three-dimensional star map allows scientists to trace the Milky Way's structure, its past collisions with smaller galaxies, and even its future trajectory. Together, these tools create a multi-wavelength portrait of our cosmic home, transforming pinpoints of light into a detailed, dynamic understanding of the Milky Way. The Milky Way has inspired awe and imagination for as long as humans have looked to the night sky. Long before telescopes revealed it as a vast spiral of stars, people around the world created stories to explain the glowing river of light stretching from horizon to horizon. In Greek mythology, it was the milk of the goddess Hera, spilled across the heavens, hence the name Galaxies, meaning milky circle. Among the Navajo, it became the Yikaizdaha, or path of the spirits, guiding departed souls across the sky. The Maya envisioned it as the world tree, a celestial road linking the realms of earth and sky. In China, the Milky Way is the Silver River, across which the cowherd and weaver girl are separated, meeting only once a year as a rain of stars. Each culture turned this band of starlight into a bridge between the human and the divine. Beyond myth, the Milky Way served a very real purpose: navigation. For sailors of the Pacific and travelers of the African savanna, its steady arc marked directions when no landmarks could be seen. Arabian desert caravans read its glow as a reliable compass, while Polynesian wayfinders memorized its seasonal position to chart ocean crossings. Even today, when science explains the Milky Way as a rotating spiral of hundreds of billions of stars, the cultural power of those ancient stories endures. They remind us that this galaxy is not only our physical home in the universe, but also a shared thread in humanity's imagination, a luminous trail connecting past and present. The study of our galaxy is far from complete. In the coming decades, astronomers are preparing powerful new instruments to uncover the Milky Way's remaining secrets. On Earth, massive next-generation radio interferometers, such as the Square Kilometre Array, SKA, being built in Australia and South Africa, will create the most sensitive radio map of the sky ever attempted. These arrays will trace faint hydrogen signals from distant regions of the galaxy, map the hidden distribution of dark matter, and detect pulsars with unmatched precision. Above the atmosphere, a new fleet of space observatories will push our vision even further. Projects like the Nancy Grace Roman Space Telescope and the proposed LUVOIR and HABEX missions aim to capture the Milky Way in exquisite detail across ultraviolet, optical, and infrared light, revealing structures and phenomena invisible to current telescopes. Perhaps most exciting is the ongoing search for exoplanets and life within our own galaxy. The Transiting Exoplanet Survey Satellite, TESS, the James Webb Space Telescope, and future missions such as PLATO and LifeFinder are scanning thousands of nearby stars for Earth-like worlds. These instruments will probe the atmospheres of distant planets for chemical signatures, oxygen, methane, and water vapor, that might hint at biological activity. Together, these efforts promise a new era of discovery. They will not only sharpen our understanding of the Milky Way's structure and history, but also bring us closer to answering the most profound question of all: are we alone? Leaving behind the grand sweep of the Milky Way, we begin our descent into a far more intimate realm, our solar system. From the cold emptiness between the stars, we glide inward toward a single point of light that has always defined our home. At the center blazes the Sun, a colossal fusion engine more than 1,000,000 times the size of Earth. Every heartbeat of warmth, every breath of air, every ripple of life on our planet owes its existence to the energy released in its core. 4.5 billion years ago, this star ignited from a collapsing cloud of gas and dust, and ever since it has shaped the dance of planets, moons, and comets that circle it. The Sun is not only a beacon in our sky, it is the lifeline of our world. Its steady radiation drives Earth's climate, powers the growth of plants, and fuels the complex web of life. Its magnetic winds carve the edges of the solar system, creating a protective bubble against cosmic rays and setting the stage for every journey we will now take. As we move closer, imagine crossing that golden ocean of light. An endless stream of photons that left the Sun's surface 8 minutes ago and now bathe our world in warmth. This is the heart of our celestial neighborhood, the hearth around which every planet, moon, and fragment of rock keeps its eternal watch. About 4.6 billion years ago, long before Earth or the Sun existed, a quiet region of our galaxy held a cold, giant cloud of gas and dust, a molecular nebula spanning dozens of light years. Within this cloud, a shock wave, perhaps from a nearby supernova, triggered collapse. Gravity pulled the cloud inward, causing it to spin faster and flatten into a vast, rotating accretion disk. At the heart of this disk, matter compressed until temperatures and pressures soared. Here, hydrogen atoms began to fuse, and a new star was born, our Sun, igniting with nuclear fire. Its powerful radiation and stellar winds blew away the remaining gas, carving a clear space and leaving behind a thin disk of material. Inside that disk, tiny grains of dust clumped together, colliding and merging over millions of years. Pebbles became boulders, boulders became planetesimals, and these planetesimals combined to form the planets, moons, asteroids, and comets we know today. The inner region, hot and dense, produced the rocky worlds of Mercury, Venus, Earth, and Mars. Farther out, where it was cooler, ices could survive, giving birth to the gas giants and their icy moons. From a single dark nebula, gravity sculpted a luminous star and an entire planetary family, a process that transformed a quiet corner of the Milky Way into the vibrant solar system that now carries life. The Sun is far more than a bright disk in our sky. It is the gravitational anchor and energy source of the entire solar system. Containing over 99% of the system's total mass, it holds the planets, moons, comets, and asteroids in their eternal orbits. Deep inside lies the core, where temperatures exceed 15 million degrees Celsius, 27 million degrees Fahrenheit. Here, nuclear fusion fuses hydrogen into helium, releasing an immense flow of energy. This energy takes thousands of years to travel outward through the radiative zone, then passes through the convective zone, where hot plasma rises and falls like a boiling ocean. Above the surface, or photosphere, we see shifting granules and occasional dark sunspots, regions of intense magnetic activity. Beyond lies the chromosphere and the Sun's shimmering corona, which extends millions of kilometers into space and produces spectacular solar flares and coronal mass ejections. From this outer atmosphere streams the solar wind, a constant flow of charged particles that races outward at hundreds of kilometers per second. This wind shapes the heliosphere, a vast protective bubble that shields the solar system from high-energy cosmic rays and creates phenomena like Earth's auroras. The Sun is not static. It follows an 11-year activity cycle, swinging from quiet phases to periods of intense magnetism marked by flares and storms. These cycles can affect satellite communications, power grids, and even Earth's climate. Without the Sun's steady fusion engine, there would be no warmth, no light, and no life. It is the beating heart of our cosmic home, a living star whose rhythms define the very environment in which the solar system exists. The inner planets, Mercury, Venus, Earth, and Mars, are often called the terrestrial worlds because they share a solid rocky composition, each formed from the dense materials that condensed near the young Sun, where intense heat drove away lighter gases. Mercury, the smallest and closest to the Sun, is a world of extremes. Its heavily cratered surface resembles our Moon, with temperatures that swing from blistering heat to icy cold. With only a trace of an atmosphere, Mercury is a silent record of the solar system's early bombardments. Venus, nearly Earth's twin in size, is shrouded in a thick atmosphere of carbon dioxide and sulfuric acid clouds. Surface temperatures soar high enough to melt lead, and crushing pressure makes it the hottest planet despite being second from the Sun. Runaway greenhouse effects there offer a stark warning of atmospheric change. Our own planet, Earth, stands apart with abundant liquid water, a nitrogen-oxygen atmosphere, and a dynamic geology that recycles its crust through plate tectonics. These conditions created a cradle for life and maintain the climate that makes our world habitable. Finally, Mars, the red planet, intrigues scientists as a possible past, or even future, home for life. Its thin carbon dioxide atmosphere and vast canyon systems hint at ancient rivers and oceans. Seasonal dust storms and icy polar caps continue to shape its surface. Together, these 4 planets reveal how diverse rocky worlds can be. From Mercury's airless plains to Venus's runaway greenhouse, from Earth's living oceans to Mars's frozen deserts, the inner solar system showcases both the familiar and the alien. Worlds forged from the same primordial disk, yet each with a story entirely its own. Between the orbits of Mars and Jupiter lies a vast region known as the asteroid belt, a sprawling ring of rocky debris that marks the boundary between the inner and outer solar system. Far from being a tightly packed minefield, the belt is mostly empty space, with millions of rocky fragments scattered across hundreds of millions of kilometers. Scientists believe the belt is a fossil of the early solar system. Billions of years ago, when planets were forming, gravity tried to assemble these rocks into another planet. But the powerful pull of nearby Jupiter disrupted the process, preventing full accretion. What remains is a collection of primordial material, ancient building blocks left almost unchanged since the solar system's birth. Among these countless bodies, a few stand out. Ceres, the largest, is a dwarf planet about 940 kilometers, 585 miles wide, with a mixture of rock and ice and evidence of past underground oceans. Vesta, slightly smaller, reveals a complex volcanic history and is thought to be the source of many meteorites that have fallen to Earth. Other notable asteroids, like Pallas and Hygeia, add to the diversity of this cosmic archive. Though the asteroids are spread over immense distances, their collective mass is only a small fraction of Earth's moon. Yet they play a critical role, delivering water and organic materials to young planets and serving as a natural laboratory for understanding planetary formation. The asteroid belt is not just a relic, it is a record of our origins. Every fragment is a time capsule, preserving the chemistry and conditions of the solar system's earliest days. To travel through it is to glimpse the raw materials from which planets, and perhaps life itself, were born. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are worlds of staggering size and complexity. Unlike the rocky terrestrial planets, these giants are made mostly of hydrogen, helium, and ices, and they dominate the outer solar system with immense gravity and intricate systems of rings and moons. Jupiter, the largest of all, contains more mass than every other planet combined. Its atmosphere is a churning canvas of ammonia clouds and violent storms, including the centuries-old Great Red Spot, a cyclone twice the size of Earth. Jupiter's magnetic field is the strongest of any planet, creating intense radiation belts and a vast magnetosphere that extends millions of kilometers. Saturn, nearly as large, is famous for its breathtaking rings. Billions of icy particles forming a delicate, shimmering halo. Its atmosphere, rich in hydrogen and helium, hosts jet streams and hexagon-shaped storms at the poles. Saturn's moons are a miniature solar system of their own, with Titan's thick atmosphere and methane seas and Enceladus's geysers hinting at subsurface oceans. Uranus tilts dramatically on its side, rolling around the Sun like a spinning ball. Its pale blue-green color comes from methane in its atmosphere, and its seasons last more than 20 Earth years each. A magnetic field offset from its core creates twisted auroras and unpredictable magnetospheric activity. Neptune, the farthest known planet, is a deep cobalt blue with supersonic winds, the fastest in the solar system, reaching over 2,000 kilometers per hour, 1,200 miles per hour. Its dynamic atmosphere forms dark storms and bright methane ice clouds, while its moon Triton is geologically active, venting icy plumes into space. These giants are not just distant curiosities. Their immense gravity shapes the solar system, steering comets and asteroids, while their diverse moons provide clues to where life might exist beyond Earth. From Jupiter's stormy depths to Neptune's icy winds, the outer planets reveal a cosmic grandeur that defines the far frontier of our solar system. The solar system does not end with the giant planets. Far beyond Neptune lies a realm of dwarf planets and countless small bodies, the ancient leftovers of planetary formation. Pluto, once the ninth planet, is now recognized as a dwarf planet, a world of nitrogen ice plains, towering water ice mountains, and a thin, blue-tinged atmosphere. Its heart-shaped glacier, captured by NASA's New Horizons probe, reveals a dynamic surface even in the deep freeze of space. Eris, slightly more massive than Pluto, orbits in the farthest reaches of the scattered disk, taking nearly 560 years to circle the Sun. Its frigid surface is coated with frozen methane, reflecting sunlight so brightly that Eris rivals Pluto despite its distance. Haumea, elongated like a cosmic rugby ball, spins so rapidly that a single day lasts less than 4 hours. A ring system and 2 small moons add to its intrigue, making it one of the most unusual bodies in the Kuiper Belt. Beyond these named dwarfs lies the Kuiper Belt, a vast icy frontier stretching billions of kilometers beyond Neptune. Here, countless icy worlds and comets orbit in slow silence, primordial building blocks preserved since the solar system's birth. From time to time, some of these icy wanderers are disturbed and fall inward as comets, their frozen surfaces vaporizing into spectacular tails of gas and dust when they approach the Sun. Even farther out, perhaps up to a light year away, astronomers infer the presence of the Oort cloud, a spherical shell of trillions of icy bodies. It is the source of long-period comets and marks the true outer boundary of the Sun's gravitational influence. Scattered among these regions are meteoroids, small rocky or metallic fragments that occasionally cross Earth's path, producing brilliant meteors, shooting stars, when they burn in our atmosphere. These dwarf planets and small bodies are more than distant curiosities. They are time capsules from the solar system's earliest epoch, preserving the chemistry and conditions of its formation and offering clues about how planets, and perhaps life, came to be. The solar system is a cosmic dance choreographed by gravity. Every planet, moon, asteroid, and comet follows a precise path set by the Sun's immense pull, while also tugging gently on each other. This web of interactions creates a delicate balance that has lasted for billions of years. Planetary orbits are not perfect circles, but ellipses, each one slightly influenced by the gravity of its neighbors. Over time, these tugs create orbital resonances, mathematical relationships where objects align in regular patterns. For example, Pluto and Neptune are locked in a 2-to-3 resonance, ensuring they never collide. Similar resonances guide many asteroids in the main belt and shape the gaps within Saturn's rings. The giant planet Jupiter acts as a gravitational shield for the inner solar system. Its immense mass captures or deflects comets and asteroids that might otherwise strike Earth. The scars of massive impacts on Jupiter's surface, like those from Comet Shoemaker-Levy 9 in 1994, are dramatic proof of its protective power. Without Jupiter's stabilizing influence, the rate of catastrophic impacts on our planet would likely be far higher. These gravitational relationships are never static. Tiny shifts in orbital distance, caused by mutual tugs or the faint drag of solar radiation, slowly rewrite the solar system's map over millions of years. Yet the overall structure remains stable, a testament to the Sun's central authority and the subtle harmony of celestial mechanics. Gravity is both the sculptor and the keeper of order, silently shaping the solar system's past and ensuring its future. The story of space exploration is the story of human curiosity reaching beyond Earth. Over just a few decades, robotic explorers have transformed our understanding of the solar system. In 1977, Voyager 1 and Voyager 2 launched on a daring mission to visit the outer planets. They revealed the active volcanoes of Io, the intricate rings of Saturn, the pale blue beauty of Uranus, and the deep cobalt of Neptune. Voyager 1 is now the most distant human-made object, traveling through interstellar space more than 22 billion kilometers, 14 billion miles from Earth. Arriving at Saturn in 2004, Cassini spent 13 years orbiting the ringed planet. It delivered breathtaking images of the rings and discovered geysers of water erupting from Enceladus, hinting at a hidden ocean. The mission ended with a dramatic dive into Saturn's atmosphere in 2017, ensuring it would not contaminate potential life-bearing moons. In 2015, New Horizons offered humanity its first close-up of Pluto, revealing nitrogen ice plains and towering water ice mountains. The spacecraft then continued into the Kuiper Belt, studying the ancient object Arakoth and sending back data about this distant frontier. From spirit and opportunity to curiosity and perseverance, a fleet of Mars rovers has rolled across dusty plains, drilling rocks and searching for signs of ancient water and life. Perseverance, launched in 2020, is now collecting samples for a future return to Earth. Today, space agencies plan bold new ventures. The Europa Clipper to explore Jupiter's icy moon, the Dragonfly rotorcraft to fly across Titan's skies, and ambitious programs to return humans to the moon and eventually set foot on Mars. Private companies are joining in, promising a new era of exploration and potential settlement. From the first flybys to interstellar travelers, these missions reveal the solar system as a living laboratory, dynamic, diverse, and still full of surprises. From ancient philosophers to modern scientists, humanity has always wondered, are we alone? Today, our quest to find life has moved beyond speculation to active exploration across the solar system. Mars remains the most familiar and tantalizing target. Evidence of dried riverbeds, ancient lakebeds, and subsurface ice suggests that liquid water once flowed across its surface. Rovers like Curiosity and Perseverance are now searching for signs of past microbial life, drilling into rocks that may preserve chemical traces of ancient biology. If Mars ever hosted life, even in microscopic form, it would prove that life can emerge on more than one world. Farther out, two icy moons hold perhaps even greater promise. Europa, a moon of Jupiter, hides a global ocean beneath an ice shell that may be twice the volume of all Earth's oceans combined. Tidal forces from Jupiter's gravity keep this ocean warm and churning, providing energy for potential ecosystems. Similarly, Saturn's moon Enceladus reveals towering geysers of water vapor venting into space, evidence of a subsurface ocean rich in organic molecules. Both worlds may harbor environments where life could survive without sunlight, drawing energy from chemical reactions on the seafloor. Saturn's largest moon Titan offers a very different possibility. Its thick orange atmosphere is rich in methane and nitrogen, and lakes of liquid hydrocarbons dot its surface. Though far colder than any earthly environment, Titan's chemistry hints at exotic forms of life that might use methane the way we use water. NASA's upcoming Dragonfly mission will fly across Titan's skies to search for the chemical precursors of life. Each of these destinations, Mars, Europa, Enceladus, and Titan, offers a unique laboratory for understanding life's potential. Whether we find microbes in Martian rocks, alien fish beneath icy crusts, or chemical clues in Titan's haze, the search will transform our understanding of biology and our place in the cosmos. Humanity stands at the threshold of a new era. For the first time in history, we possess the technology and ambition to live beyond our home planet. The Moon is our closest stepping stone. NASA's Artemis program plans to establish a sustainable lunar base by the 2030s, using local ice deposits as water, oxygen, and even rocket fuel. Private companies envision mining helium-3, a rare isotope that could fuel future fusion reactors. The Moon will be both a laboratory and a launch pad for deeper exploration. Mars is the next great challenge. Its thin atmosphere and seasonal cycles make it the most Earth-like planet in the solar system. SpaceX and international agencies propose habitats buried beneath the soil for radiation protection, powered by nuclear reactors and solar arrays. A permanent presence on Mars could begin within the next few decades, creating a second home for humanity. Asteroids and small moons contain vast amounts of metals, iron, nickel, platinum, that could supply industries on Earth and in space. Companies are developing robotic miners to extract these resources, turning the asteroid belt into a cosmic quarry. Such efforts could reduce the strain on Earth's environment and provide materials for giant space structures. These ventures demand advances in life support systems, closed-loop recycling, and long-duration healthcare. Researchers study how to grow food in lunar and Martian soil, create radiation shields, and even adapt human biology for lower gravity. The lessons learned will benefit not only future colonists, but everyone on Earth. Colonies on the Moon, Mars, and beyond will change our species forever. We will become a multi-planet civilization, ensuring survival against planetary disasters and inspiring generations with the ultimate adventure: life among the stars. Although we often imagine the solar system as a stable island in space, it is in constant motion, orbiting the center of the Milky Way like a ship on a vast galactic sea. Our Sun and its planets travel at roughly 828,000 kilometers per hour, 514,000 miles per hour, completing one full revolution around the galaxy about every 225 to 250 million years. This path carries us through different regions of the Milky Way: spiral arms rich in gas and dust, inter-arm spaces that are calmer, and subtle gravitational tides from neighboring stars. As we move, the solar system passes through giant molecular clouds, regions of intense star formation. These encounters may subtly disturb the distant Oort cloud, sending comets toward the inner planets. Gravitational interactions with passing stars or dark matter clumps can also reshape the outer edges of our system. Some scientists have explored whether this galactic journey influences Earth's climate and biological history. Periods of increased comet impacts or higher cosmic ray exposure could coincide with our passage through denser spiral arms. While these links remain debated, they highlight how our planet's story is intertwined with the larger Milky Way. Billions of years from now, our orbit will eventually bring us closer to Andromeda, the Milky Way's massive neighbor, as the two galaxies merge. The solar system will continue its voyage, carrying the legacy of life on Earth through a constantly changing galactic landscape. After journeying through the vast spiral of the Milky Way, we pause to realize a humbling truth. Our planet is only a tiny traveler, adrift in an endless ocean of stars. Yet amid this immensity, there is one place unlike any other, a world where oceans shimmer, clouds dance, and life has taken root. Now our voyage bends back toward that singular haven. We are drawn homeward to Earth, the only planet we know where life was born and continues to flourish. Here, among familiar skies and living landscapes, the grand story of the cosmos finds its most intimate chapter. Among the countless worlds of the cosmos, Earth occupies a rare and precious niche. Our planet orbits the Sun at just the right distance, a region astronomers call the habitable zone. Here, temperatures remain mild enough for liquid water to persist, neither frozen into lifeless ice nor boiled away into vapor. But distance alone is not enough. Earth's atmosphere wraps the planet in a protective blanket, balancing greenhouse gases to trap warmth while allowing sunlight to reach the surface. This delicate equilibrium keeps oceans liquid and climates stable, creating the conditions where life can thrive. Beneath our feet, a molten iron core generates a powerful magnetic field. This invisible shield deflects deadly charged particles streaming from the Sun and from deep space. Without it, solar winds would strip away our atmosphere and expose the surface to lethal radiation. Together, location, atmosphere, and magnetic protection form a perfect trinity that makes Earth a living oasis in an otherwise hostile universe. It is this unique combination that allowed life not only to emerge, but to endure for billions of years. About 4.5 billion years ago, Earth began as a swirling cloud of gas and rock fragments orbiting the newborn Sun. Gravity pulled this material together into a growing sphere. Countless collisions, some as large as small planets, heated the infant world until its surface was a molten ocean of magma. As the young Earth cooled, intense early volcanism shaped the landscape. Gigantic eruptions released gases, carbon dioxide, water vapor, nitrogen, forming a thick, hazy atmosphere. Meanwhile, water carried by icy comets and from the planet's own interior began to accumulate on the surface. Over hundreds of millions of years, oceans condensed and climates stabilized. The crust solidified, continents slowly assembled, and the first cycles of plate tectonics began. This geologic dance regulated the planet's temperature, recycling carbon and keeping Earth's surface hospitable for the life that would one day emerge. By the end of this long formative era, Earth had become a dynamic living planet, a place of oceans, mountains, and a sky capable of nurturing the earliest sparks of biology. Billions of years ago, Earth's young oceans formed a vast primordial soup, rich with water, minerals, and simple molecules. Energy from lightning, volcanic heat, and ultraviolet sunlight sparked complex chemical reactions. Gradually, these reactions assembled the first organic compounds, amino acids, nucleotides, and other building blocks of life. Within this chemical cradle, self-replicating molecules emerged, perhaps inside tiny protective droplets or on the surfaces of mineral-rich clays. These early molecular systems began to copy themselves, compete, and evolve, setting the stage for biology. The earliest traces of actual organisms appear in Archean age rocks more than 3.5 billion years old. Microscopic fossils and subtle chemical signatures reveal ancient microorganisms, cyanobacteria, and other simple life forms that transformed the planet's atmosphere and paved the way for all future species. From the quiet chemistry of a primeval ocean to the first living cells, this was the first great miracle of our planet: the transformation of inert matter into life itself. Photosynthesis and the Great Oxidation Event. More than 2.4 billion years ago, microscopic cyanobacteria discovered a revolutionary trick: photosynthesis, using sunlight to split water and create energy. A byproduct of this process was oxygen, which slowly accumulated in the atmosphere. This great oxidation event transformed Earth forever, turning its skies blue, creating an ozone layer, and setting the stage for complex life to evolve. The Cambrian explosion. Fast forward to about 541 million years ago, when life experienced an extraordinary burst of creativity known as the Cambrian explosion. In a geological instant, lasting only a few tens of millions of years, seas filled with a dazzling variety of new body plans, creatures with shells, eyes, and complex nervous systems. This period established nearly all the major groups of animals we know today. Roughly 430 to 400 million years ago, bold pioneers left the ocean. Plants took root along the shores, spreading greenery across barren continents, and soon arthropods and early amphibians followed. By carrying water inside their own tissues and adapting to breathe air, these organisms opened an entirely new frontier: the land-based ecosystems that would eventually support forests, dinosaurs, mammals, and humans. The Permian extinction. About 252 million years ago, Earth experienced the most devastating die-off in its history: the Permian mass extinction. Gigantic volcanic eruptions in Siberia pumped carbon dioxide and methane into the atmosphere, triggering runaway climate change. More than 90% of marine species and 70% of land species vanished, turning oceans anoxic and darkening skies worldwide. The Cretaceous-Paleogene extinction. Fast forward to 66 million years ago, when a 6-mile-wide asteroid slammed into what is now Mexico's Yucatan Peninsula. The impact released energy equal to billions of nuclear bombs, throwing dust and sulfur into the air. This catastrophic event wiped out the non-avian dinosaurs along with 3/4 of Earth's species, clearing the stage for mammals to thrive. Each extinction, though tragic, opened ecological space for new life forms. After the Permian disaster, reptiles and early dinosaurs evolved to dominate. Following the Cretaceous event, mammals diversified and eventually gave rise to primates and, much later, humans. Mass extinctions remind us that Earth's history is both fragile and resilient. Every ending seeds a new beginning. Evolution of primates to Homo sapiens. Earth's story of life eventually produced the primates, agile mammals that thrived in forest canopies. From these early ancestors emerged hominins, upright walkers with growing brains and skilled hands. Over millions of years, species such as Australopithecus gave way to the genus Homo, culminating around 300,000 years ago in the appearance of Homo sapiens. These early humans mastered fire, crafted tools, and developed language, creating cultures that would spread across every continent. Climate's role in civilizations. Shifting ice ages and changing rainfall patterns shaped humanity's destiny. Periods of warming opened fertile grasslands and river valleys, inviting the rise of agriculture. As glaciers retreated, civilizations blossomed along the Nile, the Tigris and Euphrates, the Indus, and the Yellow River. Climate swings tested these societies with droughts and floods, reminding us that even the greatest empires depend on Earth's delicate balance. From the very beginning, life has been an engine of planetary change. The earliest microbes released oxygen, turning a methane-rich sky into the blue atmosphere we breathe today. Over billions of years, plants, animals, and microbes have altered soils, carved reefs, and even influenced the motion of tectonic plates by driving erosion and sedimentation. Every living organism, from tiny plankton to giant forests, leaves an imprint on the planet's geology and air. Life and Earth are linked in grand biogeochemical cycles. The carbon cycle moves carbon dioxide from the air into plants, through food webs, and back to the atmosphere. Nitrogen-fixing bacteria transform inert nitrogen into compounds essential for life, while lightning and volcanic activity help complete the loop. The water cycle, evaporation, condensation, precipitation, distributes energy and nutrients, shaping climate and sustaining ecosystems. Together, these cycles create a dynamic balance, ensuring Earth remains habitable through deep time. In just a few centuries, humanity has become a geological force. Industrialization, deforestation, and the burning of fossil fuels have filled the atmosphere with greenhouse gases, pushing global temperatures higher. Ice sheets shrink, oceans warm and rise, and weather patterns grow more extreme. The fingerprints of human activity are now visible in every corner of the planet. As habitats vanish, species disappear at rates unseen for millions of years. Forests, coral reefs, and grasslands, the living systems that stabilize climate and produce oxygen, are under unprecedented strain. Each extinction weakens the intricate web of life that supports our own survival. Yet the story is not only of loss, it is also a call to action. Through renewable energy, conservation, and global cooperation, humans have the power to protect and restore the Earth's natural balance. The choices we make today, how we grow food, generate power, and care for wild spaces, will decide the future of all life on this unique world. In the deep future, our planet will face changes driven by the cosmos itself. Over the next hundreds of millions of years, the sun will gradually brighten as it burns its hydrogen fuel. This slow increase in solar energy will warm the oceans and alter the climate, eventually pushing Earth out of the current habitable zone. Meanwhile, random cosmic events, asteroid impacts, nearby supernovae or gamma-ray bursts remain unpredictable threats that could reshape or even extinguish life. Yet life on Earth has always been resilient. Microbes may continue to adapt to rising temperatures and new chemical conditions, surviving in underground oceans or high-altitude clouds long after complex life disappears. If humans endure, we may develop technology to move beyond Earth, spreading life to other planets or artificial habitats. Even as the planet transforms, the legacy of life could persist, either here in hidden niches or carried outward into the wider cosmos. After reflecting on the distant future of life on Earth, we lift our eyes back to the stars. To glimpse what lies ahead for the universe itself, humanity has built new eyes. Space telescopes capable of seeing farther and deeper through time than ever before. During the last few decades, astronomy has entered an era of breathtaking discovery. Space-based telescopes have transformed our understanding of the universe, letting us see phenomena that ground-based observatories can only hint at. Freed from the blur of Earth's atmosphere, these instruments capture razor-sharp images of galaxies billions of light-years away, record faint whispers of ancient light, and measure wavelengths, like infrared and ultraviolet, that the atmosphere blocks entirely. Placing observatories above the atmosphere is more than a matter of convenience. High above clouds, turbulence, and light pollution, a space telescope enjoys an unobstructed, crystal-clear view of the cosmos. It can observe continuously without the interruptions of day and night, and detect signals so faint they would vanish in the atmospheric glow. From Hubble to the James Webb Space Telescope, these orbital sentinels have become humanity's most powerful tools for exploring time and space. When the Hubble Space Telescope was launched in 1990, it opened a window that changed astronomy forever. Freed from the blur of Earth's atmosphere, Hubble delivered images of galaxies so sharp and detailed that scientists could measure the expansion rate of the universe with unprecedented accuracy. Its deep-field observations revealed thousands of galaxies in what once looked like empty blackness, proving the universe is far richer and more dynamic than we imagined. Hubble also became a chronicler of the stars themselves. It captured the delicate birthplaces of new suns inside glowing nebulae, and the spectacular deaths of old ones in brilliant supernova explosions. By observing these life cycles across billions of light years, Hubble helped trace how the elements that build planets and life are forged and scattered through space. Beyond its own discoveries, Hubble paved the way for the next generation of space observatories. Its technical triumphs, from servicing missions to precision instruments, shaped the design of the James Webb Space Telescope and other ambitious missions now exploring the universe. Hubble's 3 decades of service stand as both a scientific treasure trove and a guidepost for the explorers who follow. The James Webb Space Telescope, launched in December 2021, is the most powerful space observatory ever built. Its mission is bold: to look back over 13 billion years and witness the birth of the very first galaxies. By capturing faint infrared light stretched by cosmic expansion, Webb lets us peer deeper into time than Hubble ever could. But JWST's vision is not limited to the ancient universe. Its sensitive instruments can also analyze the atmospheres of distant exoplanets, searching for water vapor, methane, and other molecules that might hint at life. For the first time, astronomers can study the chemical fingerprints of alien skies with extraordinary precision. To achieve these feats, Webb was placed far beyond the Moon at the second Lagrange point, or L2, about 1.5 million kilometers, nearly 1 million miles, from Earth. Here, Earth and Sun's gravity balance perfectly, allowing a stable orbit with minimal fuel. Its 6.5-meter primary mirror, made of 18 gold-coated segments, unfolds like a giant flower to gather more light than any previous space telescope. When JWST released its very first deep-field image in July 2022, the world saw galaxies from over 13 billion years ago, tiny arcs of light whose journey began near the dawn of time. This single frame revealed thousands of ancient galaxies, some distorted by gravitational lensing, proving that the telescope could peer deeper into cosmic history than any observatory before it. Not long after, Webb turned its golden eye toward distant worlds. By splitting starlight as an exoplanet crossed in front of its star, JWST captured the first high-resolution spectrum of an alien atmosphere. These delicate fingerprints revealed water vapor, carbon dioxide, and hints of complex chemistry, critical clues in the search for life beyond Earth. The telescope also unveiled the breathtaking nurseries where stars are born. Its infrared gaze cut through clouds of dust to reveal the Carina Nebula's towering pillars and hidden newborn suns. These images show stellar creation in action, allowing scientists to watch the sculpting of stars and planets inside dense interstellar clouds. From the oldest galaxies to the youngest stars, Webb's first images proved that its mission had begun with a triumph. Each observation rewrote textbooks and set the stage for decades of exploration, turning distant, invisible phenomena into scenes of astonishing clarity. Beyond a single golden mirror lies a fleet of complementary eyes. Where JWST excels at deep, high-resolution infrared views, other observatories fill in the rest of the spectrum and the rest of the sky, revealing the coldest dust, the hottest plasmas, the widest maps, and the fastest changes. Together they turn isolated images into a living, multi-wavelength story. High on the Atacama Plateau, the Atacama Large Millimeter/Submillimeter Array, ALMA, listens to the faint glow of cold dust and molecules just a few degrees above absolute zero. ALMA resolves protoplanetary disks into rings and gaps, places where planets are taking shape, and traces complex organic molecules in stellar nurseries and cometary comae. Paired with JWST, ALMA supplies the initial conditions, gas mass, chemistry, dust grain growth, that JWST then follows as those clouds warm, collapse, and ignite into stars and planets. The Chandra X-ray Observatory reveals what infrared cannot: million-degree plasmas around black holes, neutron stars, supernova remnants, and shock-heated gas in galaxy clusters. X-rays map accretion, jets, and feedback, the energy that sculpts galaxies from the inside out. Together, Chandra and JWST connect hot engines to cool reservoirs, Chandra shows where energy is injected. JWST shows how dust and stars respond, completing the feedback loop that governs galaxy growth. The European Space Agency's Euclid is built for cosmic cartography. With sharp, wide-field imaging and spectroscopy, it maps weak gravitational lensing and large-scale structure over vast areas of sky. Where JWST offers pencil beam depth, Euclid delivers breadth, statistical power to probe dark matter and dark energy through the shapes, clustering, and redshifts of billions of galaxies. Euclid sets the cosmic context that frames JWST's deep fields, not just what early galaxies look like, but how the web that hosts them evolves. On Cerro Pachón in Chile, the Vera C. Rubin Observatory will run the Legacy Survey of Space and Time, LSST, a 10-year movie of the sky. By scanning the heavens night after night, Rubin will find transients and movers, supernovae, kilonovae, tidal disruption events, variable stars, and near-Earth asteroids. It is the cosmic early warning system that flags fleeting targets. JWST then zooms in with infrared spectroscopy to read their chemistry and physics while the moments still burn bright. One universe, many windows. ALMA's cold dust, Chandra's hot fire, Euclid's grand map, Rubin's restless sky, and JWST's infrared detail form a symphony across wavelengths and timescales. Only together do they reveal the universe as it truly is: cold and hot, ancient and immediate, vast and vividly alive. Science and culture in the age of cosmic imagery. The newest portraits of the universe, spiral galaxies laced with dust, infant stars swaddled in glowing gas, and planets silhouetted against distant suns, do more than fill data archives. They ignite curiosity across every discipline of science. Astrophysicists refine models of galaxy formation. Chemists study the fingerprints of molecules in alien atmospheres, and planetary scientists re-evaluate the recipe for life itself. Each James Webb Space Telescope spectrum or Atacama Large Millimeter Array map becomes a shared laboratory for thousands of researchers worldwide. But the influence reaches far beyond research institutions. Artists, writers, composers, and filmmakers draw directly from these images. Nebula color palettes seep into fashion and digital art, while the rhythm of cosmic expansion inspires new music and literature. The pictures become modern myths, renewing our sense of place in a living cosmos. For the public, these observatories serve as cosmic storytellers. High-definition images travel instantly across social media, classrooms, and planetariums, turning complex astrophysics into moments of wonder for millions. This democratization of discovery reshapes our worldview, reminding us that Earth is a small oasis in a vast, evolving universe. Ultimately, every deep-field mosaic and exoplanet spectrum reframes humanity's perspective. They challenge old boundaries between science and philosophy, inviting us to see the universe not only as an object of study, but as a source of meaning. In doing so, modern space observatories become bridges between knowledge and imagination, altering how we understand both the cosmos and ourselves. After exploring the latest cosmic discoveries through powerful new telescopes, we look even further ahead, to the destiny of the universe itself. What will become of the stars, the galaxies, and the very fabric of space-time? Join us as we journey into the far future to glimpse the ultimate fate of the cosmos. Imagine standing beneath a sky scattered with billions of stars, knowing that every galaxy, every cluster of light, is part of a story that will one day end. Cosmology, the science of the universe as a whole, asks a question as old as human curiosity. How will it all conclude? Scientists now understand that the universe had a beginning, the Big Bang, but its ending remains one of the greatest unsolved mysteries. Will space expand forever until every star fades into darkness? Could gravity someday pull everything back into a final fiery collapse? Or might an even stranger fate, something we have not yet imagined, await? This is more than an academic puzzle. Predicting the ultimate destiny of the cosmos forces us to test the very laws of physics, to understand dark matter and dark energy, and to confront the limits of time itself. It also carries a profound philosophical weight. Knowing how everything ends reshapes the way we see our own fragile moment in cosmic history. After billions of years of evolution, our universe is not slowing down. It is speeding up. Observations of distant supernovae and the cosmic microwave background reveal that space itself continues to stretch faster and faster. The invisible force driving this runaway growth is known as dark energy, a mysterious pressure that counteracts gravity. As galaxies rush apart, their light will drift farther into space and fade beyond detectability. First, star formation will decline as interstellar gas is used up. Then, over trillions of years, existing stars will burn out one by one, leaving behind only cold remnants, white dwarfs, neutron stars, and black holes. Eventually, even those black holes will evaporate through a slow quantum process called Hawking radiation. The final picture is haunting. A universe that grows ever larger and emptier, its temperature approaching absolute zero. Every galaxy an isolated island, adrift in a dark, frozen void. This scenario is sometimes called the heat death of the cosmos. A silent, endless night where time itself stretches toward infinity. Not all cosmologists agree that eternal expansion is inevitable. Current observations describe a universe driven by dark energy. But if that mysterious force changes its strength over time, very different futures could unfold. If dark energy grows stronger, the expansion of space will accelerate without limit. Galaxies will tear apart, then solar systems, then planets, and finally even atoms and subatomic particles. In this scenario, every bond in nature breaks as the fabric of space-time itself rips apart. If, instead, dark energy weakens or reverses, gravity could regain control. Over unimaginable timescales, the expansion would slow, halt, and reverse. Galaxies would rush back together, the night sky growing ever brighter until everything collapses into a final, fiery implosion, a reverse Big Bang. A third path mirrors the eternal expansion, but focuses on the slow fade of energy. Stars burn out, black holes evaporate, and the universe drifts toward a cold, featureless darkness where no new complexity can form. These possibilities remind us that the ultimate fate of the cosmos is still an open question, bound to the unknown nature of dark energy and the deepest laws of physics. What science says today. Modern cosmology now combines decades of observations to narrow the possibilities for the universe's fate. Astronomers study three key pillars of evidence: 1. Type Ia supernovae. These standard candle explosions reveal that the universe's expansion is accelerating. Their precise brightness allows scientists to measure cosmic distances and confirm the presence of dark energy. 2. Cosmic microwave background, CMB, maps. Satellites such as Planck and WMAP have traced the faint afterglow of the Big Bang, giving us a detailed picture of the universe's composition. Roughly 68% dark energy, 27% dark matter, and only about 5% ordinary matter. 3. Large-scale structure surveys. Galaxy redshift catalogues like Sloan Digital Sky Survey, SDSS, map the cosmic web, showing how dark matter's gravity sculpts the distribution of galaxies. Together, these lines of evidence point strongly toward a universe dominated by dark energy, which drives eternal accelerated expansion, a scenario often linked to heat death. Alternative endings, such as the Big Rip or Big Crunch, remain theoretically possible, but current data favor a cosmos that keeps expanding, cooling, and fading for trillions of years. When we contemplate the ultimate fates of the universe, we confront more than physics. We confront time itself. Cosmic endings make the arrow of time tangible. Stars ignite and fade, structures assemble and dissolve. Order gives way to entropy. In this vast chronology, our own lifespans are brief. Yet this brevity clarifies rather than diminishes meaning. The finite sharpens awareness. A moment of consciousness against an ocean of darkness is not less precious, it is more. These scenarios also refract the question of life. If the cosmos ultimately cools and dims, then every living system is a temporary island of negentropy, an oasis where matter briefly organizes into thought, memory, and care. That impermanence does not empty life of significance, it assigns it. To keep a biosphere flourishing, to widen the circle of flourishing beyond Earth, becomes a project worthy of our one luminous interval. And what of us? A species that can ask these questions. In learning the laws that govern galaxies and atoms, we become the universe becoming self-aware. Science and art are two gestures of the same astonishment. One measures, the other translates wonder into meaning. With that awareness comes responsibility to steward our planet, to preserve knowledge, to choose compassion over conquest as we reach for other worlds. Whatever the cosmos's final act, eternal expansion, collapse, or a quiet fade, the ethical constant is clear: care in the present. We cannot command the end of time, but we can cultivate wisdom, reduce suffering, and protect the only cradle of life we know while we build the next. In this way, the prospect of an ending is not a defeat but a directive. To live attentively, creatively, and kindly within the brief window that the universe has opened for us. We have traveled an incredible journey through time and space, from the first sparks of the Big Bang to the mysterious future of the universe. And now comes a quiet moment. May these stellar stories inspire you to cherish your own world and never lose your sense of wonder. If you enjoyed wandering among the stars as much as I did, hit subscribe, leave a like, and share this video. There are many more amazing facts ahead, and I don't want you to miss the next adventure. So stay with us. Our next cosmic journey is already waiting.